Good afternoon and welcome back to the workbench. So today this is going to be a little bit of a sort of follow-up video to a video I did recently, which is the KiCad tutorial. I suppose really it's KiCad, but I didn't know that's what the correct pronunciation was when I first started using it, so I've just kind of got used to saying KiCad. So apologies to anyone who is annoyed by that, but that's just kind of how it's ended up. But anyway, yeah, so 2 videos ago I did a sort of a quick sort of tutorial sort of thing about KiCad and designing a board in that from sort of start to finish. A little power supply which is here, so I've actually finished making that, and I've just been testing it out. And this video is about sort of the almost inevitable mistakes or errors or things you end up having to change that come about during the process of designing something and making it from scratch. And yeah, just showing like what you can do, I suppose, and just what happened basically. So you know, sometimes you get, you know, really bad errors, really big problems, you know, the thing doesn't work at all, which is funnily enough the case originally with this thing. This is sort of a rebuild, like I said, of in the previous video. I said this is like a rebuild of the original version, which was on this bit of strip board here. I've got a photo somewhere of how it used to look, but it never worked properly. The negative voltage regulator, which is supposed to be negative 15 volts, would output like negative 20, and it was just not working, and I don't know. Yeah, so I'll just go into that in a minute, but yeah, so I ended up just stealing all the components off the original board, and I put them on the new one. And the thing does work now, but I'll explain exactly what happened and why it didn't work before. So the original version I built of this was, I suppose, about 20 years ago, and I was pretty inexperienced at the time, and didn't really know what I was doing. So there were a few mistakes in that to start with. Mostly, well, there were 2 mistakes. There was one mistake which was why the thing didn't work, and there was another mistake which could have been a problem but was just probably wouldn't have been an issue, but was still a mistake that wasn't very good. Which was that the layout I had of the board, the decoupling capacitors for the input decoupling capacitors for the regulators were like at the opposite end of the board to the regulators. You know, they should have been right next to the regulators, but they weren't. They were like on the other side of the board, and that was because of something I'd read in an electronics book about having decoupling capacitors where the power supply rails enter the board, and I got that confused and thought it had to be on the output, and I just did. It was just silly. I mean, you know, I was very young at the time. I didn't really know. I was just learning, so it's to be expected. You make silly mistakes like that. Nowadays, obviously, I know that, you know, the decoupling capacitors for integrated circuits need to be right next to the integrated circuits as close as possible. Otherwise, you know, they're not going to do anything. The further away they are, the less effective they are. So you have to design your layout properly. It was just a bad design, but that wasn't why the thing worked. I mean, you could argue maybe the regulator was oscillating because the capacitor was too far away, and that was causing the high voltage. Well, yes, that could have been it, but that wasn't the problem specifically for that particular thing. But it's a possibility that could happen. Some voltage regulators, especially I think low dropout ones, probably not the ones I was using, but some of them will oscillate if you don't have the correct decoupling capacitors near them, so it's definitely a problem. But anyway, this particular one, I was using the 7915 and the 7815 dual to make a dual supply of negative and positive 15 volts. And what I'd done was I was using this transformer here, same one, which I've got wired up. So I'll show in a second. So this one is a Dick Smith M2854. Obviously Dick Smith don't make anything like this anymore. It's a 12 volt center tap transformer, so I mean it's, well, 24 volt, sorry. So it's a 12-0-12 transformer, so it'll give you 2 split windings of 12 volts each, or one of 24. And I figured, well, I wanted negative and positive and negative 15 volts, so obviously I couldn't use it center tapped because 12, you know, you can't, that's not enough power. So I figured, well, I'll cut the center tap wire off and just use it half-wave rectification from just the full voltage, 24 volts across it. And that makes sense, you know. I mean, it's not ideal. It's not really the best option. If you can get a transformer with the right voltage and you can use the center tap, you can use full wave rectification, which is much more efficient. But for this, I only wanted it to power a little preamp, which is basically one op amp and not much else, and it only draws about 10 milliamps. So using half-wave rectification is not really an issue because it doesn't matter. It's such a low current, there won't be really a problem. It's just that the voltage, the ripple voltage will be a lot higher because you're only rectifying half of the sine wave. So one half of the sine wave goes to one capacitor and one to the other instead of both halves to each if you had a full wave rectifier. So yeah, but that still wasn't the problem though. Half-wave rectification is perfectly valid. It just means you can't draw as much current before you start getting a high ripple, and so you need larger transformer and larger filter caps, basically to get rid of that ripple if it's going to be too high, if your load is high. So yeah, it's just a thing. Like I say, for this case though, such a low current doesn't matter, so it's not really a problem. But the problem was, my assumption back then was that as it was not knowing really that that AC voltage and DC voltage are rectified are obviously different. I just sort of assumed that you put 24 volts, you get 24 volts out of the transformer, you get 24 volts DC after you rectify it, and then that makes sense, and it would all work. But the thing is, of course, if you don't know already, you can see where this is going probably. 24 volts AC does not equal 24 volts DC when you rectify it. In fact, it increases quite substantially. So basically, you take the voltage 24, whatever your AC voltage is, and you rectify. If it's a sine wave, obviously, for a complex wave or something else, it would be different. But for a pure sine wave, you can basically cheat. I mean, there's a formula for it, but you can basically cheat and multiply it by 1.414, and that'll give you the rectified DC voltage. So if we do that, so 24 approximately, and then of course this is going to vary depending on your mains line voltage as well. I mean, this transformer is spec'd from 230 to 240 volts, and I think my voltage is 237 or about that, so it's going to be on the higher end as well. So if we take 24 and multiply that by 1.414, we actually get 33.9 volts. Now that's significantly higher than 24. It's 10 volts higher, just almost. So you know, that's for a start. There's that. The other thing is, obviously, that is maybe it may be spec'd at the lower end of the voltage at 230 volts, just to say, you know, we guarantee 24 volts all the way down to 230 volts, and if you run it at 240, you're going to get even more. So if I actually hook up my voltmeter, actually I probably should do this close up. Sorry, yeah, it's a bit it's not very good. Okay, hang on, I'll switch the camera around and I'll do that. Okay, so here's the transformer up close, and you can see it's rated 12 volts AC, which is per half winding. So from the center tap to each red wire will be 12 volts, and across both it'll be 24. And that's from that's rated at 230 to 240 volts primary. But here's the thing: I am going to assume that this 12 volts rating is at the because it's rated as a 12 volt transformer, it's going to have to do 12 volts all the way down to 230 volts, which is what it's rated at. But my mains voltage is higher than that. I think it's about 237. In fact, I can just check that right now. So I've actually got the little terminal block here, which this is going into. So these screws, obviously, they're recessed inside this, so it's not really a problem. But these are live. So if I just take this little meter here and stick the probes down the holes and access the screws, we can see. Yes, we can see my. Whoops. We can see the mains voltage here is about 230. It's peaking at 237. I'm probably not getting very good contact here, but you see it's definitely on the higher end, closer to 240 than anything else. So this transformer, if we actually measure the output now, just get this out of the way. If I measure the output of this, we can see, sorry, these probes are all tangled up now. If I measure the output of this, we actually get almost 26 volts. Yeah, 25, almost 26. So for a start, it's higher than what it says on the label because it's running at a higher input voltage. So if we then have a look at this, I'll just unplug it so I don't short the output wires. So if we go back to the calculator here, you'd expect the rectified DC to be 33.9 if this was outputting exactly 24 volts AC, but it's not. It's doing about 26. 26 times 1.414 is 36.7. So suddenly we've got, 36.7 volts. And the thing that I didn't know at the time, 20 years ago when I first designed this thing, is that these voltage regulators have a maximum input voltage rating. And funnily enough, it's about 35 volts, I think, for the 7.9 and 7.800 series. 36.7, that is over the input rating of these regulators. So the problem with my original layout, my original design for this, was the regulators were just being overvolted, and the positive volt one was seemed to be handling it okay. Because I guess it was pretty close to the 35 volt maximum, but the negative one just was obviously breaking down. The pass transistor inside was just breaking down and was just outputting the full, or close to the full input voltage. So yeah, that's what was going on there. So I realized obviously that I couldn't use this transformer directly with the with this board as it was. So I decided, well, I need to figure out some way to get the input voltage down and make sure it has a good margin for the entire voltage range this thing expects as an input. So there's basically two sort of ways I could have done that. I could have had another pair of regulators of high voltage in front of these to sort of pre-regulate and then regulate again. That's one way of doing it, but that's expensive and complicated because you have to have two lots of regulators. The other option would be a simple sort of Zener diode and pass transistor arrangement on each rail. So you maybe pre-regulate down to say 25 volts with that arrangement. So it requires a high voltage transistor and a correct Zener diode. And the problem with that is there's no room on the board really, and the project I'm doing this for needs to fit in a particular sized box because it's what I've got, and the power supply board can't really be much bigger than this. So despite the fact that I don't want to respin the board and make it again, I also can't really make it bigger, so it wouldn't really fit. Even though I do technically have room here, it's just, well, I don't really want to. It's just too much hassle. So I thought, well, the best way to fix this problem is just to be really sort of, well, so cheap and bodgy and shove in a resistor in the input. So that's what I've done. I've stuck this 100 ohm resistor in, which is just a value I came to from, it could be a little bit lower I guess, but it works. It's a value I came to basically because it was what I had on hand, and I figured that I'd give it a try and it works perfectly fine. So it drops about 5 volts AC at the standard load, and not much power dissipation. It's a 3 watt resistor. I think it's barely dissipating a watt or even less, so no problem with overheating or anything. But yeah, I've basically had this hooked up. Of course, there is one problem with that design, and that's with having the series resistor. It won't actually it won't reduce the voltage by itself, or at least it won't reduce the voltage when there's no load on it. So if these regulators are not powering anything, then the input voltage will just rise up to the full voltage, and the outputs won't work. So I had to bodge in this LED and this resistor here, which I just used some of these spare pads that I haven't been using. And that just goes, provides like a little 10 milliamp load which goes from one rail to the other. So as well as having like a minimum load for the circuit, which means that this resistor here will actually work. It also means I've got a sort of power indicator LED going across both rails, which means that if either rail fails, then the LED goes out, and I'll know that there's something wrong. So, but yeah, it's not really doing anything else apart from that. Of course, the load of the op-amp itself would also provide a minimum load that would solve the problem. But I figured I wanted to have something there that would be guaranteed, so that testing this on the bench and playing around without any outputs connected, it wouldn't blow up or anything. So yeah, so I've done that. And I mean, and these capacitors I had lying around, these were 50 volt parts, 470 microfarad. At the about 20 milliamp load out in the outputs here, from the op amps, 10 milliamps and 10 for this LED. I get about 500 millivolts ripple, I think, on these, which is perfectly acceptable because the voltage across these is quite high. So I figured, worst case scenario, if this goes open circuit, if this resistor goes open circuit, something, and the load is disconnected, then the voltage will rise up. So yeah, 50 volt parts makes sense, because they will handle the full rectified voltage from that if there was no load on the circuit at all. And I think that the reason this regulator only still works is because I never actually tried loading it down. My initial tests when it was on the previous bit of board here, I always just tested it open circuit. So I think the 7915, the pass transistor inside, was probably breaking down and allowing current through, but because there was no actual load, then I don't think it actually failed. It was kind of current limited, and so nothing bad happened to it. So it's still perfectly usable. It still seems fine. So it seems to work. So that's good. So electrically, that was what was wrong with the original design, and this has got nothing really to do with the circuit board layout which I made. It's that's perfectly fine. There's no issue with that. The issue was just using this transformer. Basically, it would make more sense to get like an 18 volt transformer and just run that straight into here, and then you wouldn't have to bother with having this resistor and all that. But yeah, and you could have a full wave rectifier and everything. But it's just, this transformer is what I had, so I had to just make a sort of a bodge around it to get that to work. So yeah, I just figured, I originally intended to use this, so I wanted to use it. It's it's only 150 milliamps. It's not really much good for anything else, but for this it's perfect because the preamp doesn't draw much current, and I think when you factor in everything out of this, I think this thing runs about 50% capacity. I think it's about 70 milliamps in total from the AC side, because obviously you have bursts of current when these capacitors charge up, when the because they discharge a bit when the input sine wave goes down, and when it goes up, then these have to recover. So the average sort of current draw of that is about 70. So yeah, it's just not worth it trying to find another transformer. This is a nice small transformer as well, but yeah, it seems to be rated perfectly fine, so I'm just going to use that with this resistor, which sort of solves that problem. The other problem with this, though, is actually in the board layout itself. So well, not really a problem with the layout, just a couple of minor things. One was that these pads here for the variable resistors, which I wanted to put in, these actually violated the clearance significantly, which I created. I chose like a 1mm clearance, which is ridiculous, but I just wanted to make it so, for a home edge board, if anyone wanted to do this as like a first off board, then it would be easy because it's such a large gap, and it's going to be easy to fix up if something goes wrong with the transfer. But this is about 0.2mm, I think, between these two pads here. I've got a close-up I can put in. So I changed the design from circular pad to oval pads on this, and was able to get the clearance back to what it should have been. So that's not a big deal. It's easy to change in the design. The other problem was these mounting holes. I put these 4 mounting holes on the edge. Ignore this one. This was in the blank PCB material already when I got it, so it's just random hole, irrelevant. But I decided I want 4 mounting holes on the outside. These two are fine, they're nice in the corner, and this one will be fine for this particular version, but this one, which is a bit cracked because I had a bad drill bit, was a bit blunt, and it cracked the board. But the problem with this basically is I chose M3 screws. We have a lot of them lying around, but if you put this in here, you can see the screw head almost touches the lead of that diode there. So that's definitely a problem with the board layout. I forgot to check the clearance between the obviously the clearance for the hole for the thread is fine, but for the head or a nut, if you had it around the other way, there's just not enough room. So to solve that, I'm going to change it so this diode is vertical basically and is moved away from the edge, because I can't really move this hole or anything. I could have drilled like a hole here and moved it over if I really wanted to, but for this particular thing I'll just use I'll have the screws coming up this way anyway, and I'll just use a nylon nut in this particular one, so it's not a problem of shorting out to anything, because these will be bolted to the case, and don't want that that will sort of short the positive rail to ground, which won't be very good, so potentially. So yeah, so that's of course I could also fit the diode to this pad here. I've got a spare pad for the other diode. Like I said, I'm only using one diode per side because it's a half-wave rectifier, so I could actually take this lead from this pad and mount this diode vertically and have it going from there to there. But that's not necessary. Like I said, just use a nylon nut on this particular screw, doesn't matter. But I'll change the board layout, fix the pads for these for the variable resistor for here and here, just to make it consistent with all the rest of the clearances. I mean, it's still perfectly acceptable as a home etched board. 0.2 is fine. I've done ones down to about that anyway before, and it's not an issue, but for some people it could be a problem, so I'll fix that. And yeah, just this screw. Surprised I didn't catch that before, to be honest, but yeah, it's just a bit too close to that lead, so I don't like that at all. Okay, so there's the transformer reconnected to the supply, and if I plug this in now, you can see the light comes on and nothing explodes, which is a good start. So yeah, it's all working just fine, and I've had this running for several hours before, and everything just gets slightly warm, which is what you'd expect. Nothing's overloaded in any way. It's all just perfectly fine. So if I bring this in here, stick something under this. There's a bit better. We can see that the got this ground there. Center pin is ground. If I have a look at this, we've got 15 volts coming out of the top regulator, 15.1, but It's close enough. And at the bottom we got -15. So it's all running as expected, and I have tested this with the preamp board, and it seems to work perfectly fine. So now basically, yeah, just have to re-edit the design files to solve that little technicality with the screw here in that corner, and obviously this one as well, because that won't work if you were using both diodes. I haven't tested this design with the 337, obviously, so I can't guarantee it would work with that at this point, but I don't see why not. I maybe actually will make another one of these at some point, just to have like a sort of a spare board that I can use, but yeah, it does seem to work though otherwise. So there we go. Yeah, that's the finished board. It does work, and I just had to solve that slight problem of using what's kind of is an incorrect transformer for what I want to do, but I've added this resistor in and everything should work basically. I see it's very unlikely that this minimum load resistor and LED and the op amp and everything would all go open circuit at once and cause the voltage regulators to potentially fail. I think it's very unlikely. It's not really a good design, I guess. It's sort of more just like a bodge to fix this problem. Obviously, if you were designing this from scratch, if you were doing a production thing, this would be considered a prototype, and you'd say, well, this is no good. We're going to have to use the LM317, the 337 instead, because the voltage differential from that, it has a maximum voltage differential from input to output of 40 volts. So if I'm, putting 50 volts in, getting 15 volts out, then that's a differential of 35. So that's within the tolerance. It's fine. This isn't even 50 volts input. So yeah, I could use these. I could use those regulators and not have to use this resistor. But I figured, these parts were already lying around. They seem to be working fine. I'm just going to use these. Add a resistor. It's a bodge, but it works. It lets me use this transformer, and yeah, it's just easier and cheaper and just basic. But if you're actually doing a proper production thing, it's not a very good solution. Because like I said, if that minimum load resistor fails, then the voltage goes up. It could be a problem, especially if you had like really expensive circuitry on the output, which may not have a load all the time. It may switch on and off or something. I mean, not likely, but debatable. If you had something like that, you'd want to make the power supply a lot better than this. But for what this is, for a bit of a bodge, it'll work fine. It's not great, but to get around the problem, a better option would be, like a pre-regulator or just a different transformer or different regulators, basically. But yeah, just goes to show, even the most basic designs, there's always something can go wrong, something you have to change. So if you are building a circuit from scratch, if you are designing something from zero and you want to, do it. I mean, if you're making a one-off for yourself, you might just have to hack a few things like this, but yeah, if you're doing like a production thing, you really need to, you probably will end up making a few prototypes. You may have to do a few revisions, you may have to go back and change things, and especially like with these mounting holes, I mean the clearances for things, that's probably one of the biggest things I've actually had a problem with, is just forgetting to check clearances on components and having to squeeze something in that or work around something that wasn't perfect. Not much of that kind of stuff, but it is easy to forget, because a lot of times there's so many things that have to go next to each other, and you sometimes forget about the height of something or the width, or you check one aspect of it. I mean, like I checked the actual mounting holes, the drill size was fine, that was good, but forgot the fact that the actual screw head is larger than the hole, and yeah, a bit silly, but hey, everyone makes mistakes, so always a good idea. If you're definitely building something from scratch, bear that in mind. Things are you're probably gonna make a mistake somewhere, and hopefully it won't be a big one. Hopefully it will be fixable, or you can work around it somehow. But just expect that, and also realize that, yeah, I mean, these things take a while to build. It takes it's not an instant thing. It's not like software. If you're coming from like an area where software is what you've been doing, you're suddenly going into hardware, then yeah, like it takes a longer time. You can say that, you know, the compilation time of a circuit can be considered days or weeks even, depending on how it's being done. If you're outsourcing to like a factory or something, if you're doing proper production or something, it's, you know, so you get your prototypes back from the factory, and then you know, something doesn't work, you got to redo it and send off for some more prototypes, and it could be weeks, depending on what you're doing. So yeah, I always think to factor into account and make sure of that. But I guess a lot of the stuff can be summed up quite well with that old carpenter's rule of measure twice, cut once. So just to check everything, you know, print out your board, check the clearance of everything. When I say print out the board, I mean print it out on paper, check the clearance of everything, check that things actually fit, check that pads line up with component leads, stuff like that. Yeah, it can save you a lot of time. There's definitely a lot of problems I've fixed before I made the board that I was able to catch by just printing out a paper copy and just, like, you know, sitting the components on the piece of paper and just looking at where the leads go and saying, you know, oh, you know, the spacing of this was actually wrong, and, you know, this lead is slightly off to the side and stuff like that, or we can't put that capacitor there because that would interfere with the body or some other component, or something like that. So, you know, I mean, these stuff like that happens. The more you test, the more you check first, the less likely you are you're going to have some major design problem that will render the board unusable, or, you know, or anything like that. So just a sort of bit of just a video to say that, you know, mistakes happen, things have to be changed, prototypes are prototypes, and yeah, that's just how it works. Some things are easy to fix, some things aren't. So yeah, the next thing for me will be to actually get the preamp all set up and working, because the original version I made was designed to directly preamp a tape head. I was going to originally try and build my own tape deck at that time, but I had like the transport and everything, actual mechanism and everything. I had that, and I was going to hook up its own preamp and power supply and everything for it, but it never happened because of the power supply issue, and just ended up doing other stuff. But yeah, so I have to change like some of the feedback components, because the frequency response is all designed for tape, and it cuts out the high frequencies, and it sounds awful if you use it direct. So I got to fix that up. But once I get that, you know, this power supply all seems to be alright. So once I'll probably make a video about that as well, of changing the components and that and stuff. But for now, I'm just sort of got the power supply done, got that working, and I think I can say that I can do minor edits on this design, and then probably just release it, because everything should be fine. So yeah, there we go. That's kind of the other half of the process of designing something, is prototyping, testing, and fixing errors, and then having to redo the thing and remake it. I mean, obviously I don't have to remake it, but, you know, if this was a production thing, you'd want to redo it if you know, to solve this kind of problem, because it's just a bit of a bodge here. But for me, it's fine. So yeah, anyway, well, there we go. Hopefully that was interesting. Hopefully provided some sort of entertainment or something. So yeah, I'll see you next time.